Let your shoulders drop gently, as if releasing the weight of the entire day. Allow your breath to settle into a slower, deeper rhythm, like waves finding their natural pace on a quiet shore. Tonight, we drift together toward a simple question that carries something vast within it. Can two black holes merge into one? This sounds like physics, but as we'll discover, it's really about the nature of unity itself, about what it means when boundaries dissolve and two become one. I'm curious, where you are right now, perhaps in a quiet room with rain outside or wrapped in warmth. Wherever you are, we're sharing this moment under the same sky. If this resonates with you, feel free to subscribe, leave a gentle comment, or offer a soft like. No rush, only if it feels natural. Now take one more slow breath with me and let us begin. But first, we need to understand what a black hole really is, because you cannot know if two things can become one until you know what each thing is alone. So, we start with a single black hole, and we ask, where did it come from? Somewhere in the night sky, a star is dying. It doesn't cry out, it doesn't flicker with warning. It simply reaches the end of its long burning life. And to understand black holes, to really know what they are and where they come from, we must begin here, not in darkness, but in light, because every black hole begins as a star. Picture one now, massive, luminous, ancient, 25 times heavier than our sun, maybe more. Its body is made of hydrogen, its heart a fusion engine that has burned for millions of years. The star is not calm. Its surface churns with magnetic storms with flares of heat and light. But deep inside at its core, a delicate balance holds. Gravity pulls inward, fusion pushes outward, and the two remain locked not in battle, but in quiet agreement. This balance is everything. It's what allows a star to shine. It's what keeps it from collapsing under its own enormous weight. For most of a star's life, this dance continues steady and patient. Hydrogen fuses into helium, releasing tremendous energy. That energy radiates outward, creating pressure that holds the star up against gravity's constant pull. The star glows. It warms planets that might circle it. It sends light across the cosmos. But no fuel lasts forever. Eventually, after millions or billions of years, depending on the star's size, the hydrogen in the core runs low. The star begins to fuse helium into carbon, then carbon into heavier elements, oxygen, neon silicon. Each stage burns hotter and faster than the last. The star tries to maintain the balance, tries to keep pushing back, but there comes a point always when even this cannot continue. When the core begins to fuse iron. Iron is different. Fusing iron doesn't release energy, it consumes it. And so the star's engine, which has powered it for so long, begins to stall. The outward pressure weakens, and gravity, which has been waiting patiently all this time, begins to win. What happens next is almost unimaginably fast. The core collapses. In less than a second, all that mass, all those layers of elements built up over millions of years, caves inward. Atoms are crushed together. Protons and electrons are squeezed into neutrons. The matter becomes denser than anything you can picture. A teaspoon of it would weigh more than a mountain. The outer layers, no longer supported, fall inward too, but they bounce off the collapsing core and explode outward in a supernova, a blast of light brighter than an entire galaxy. For a few brief days, this dying star outshines everything around it. A last brilliant flare before the silence comes. And what remains at the center depends on how massive the star was. For smaller stars, a white dwarf forms, hot dense but stable, a quiet ember that will cool slowly over billions of years. For heavier ones, a neutron star, a ball of neutrons, perhaps 20 kilometers across, spinning rapidly, so dense that a handful would outweigh a mountain range. But if the star was truly massive, if it started with more than about 20 or 25 times the sun's mass, then even neutrons cannot hold back the collapse. The core continues to fall inward, beyond atoms, beyond neutrons, beyond anything our physics fully understands. And there, in that final inward plunge, a black hole is born. It doesn't explode into existence. It doesn't announce itself with light or fanfare. It simply becomes something new, a region of space where gravity has become so strong, where the curvature has become so steep that nothing can escape. Not light, not time, not matter, not information. A place where the escape velocity exceeds the speed of light itself. That's what a black hole is. Not a hole in the way we imagine holes in the ground. Not empty, not even dark in the way night is dark. It's a place where the geometry of space has folded inward so deeply that all paths lead to the center. Let me help you picture this, because the mathematics is beautiful, but the image is simpler. Imagine space not as nothing, but as something, a fabric. Einstein taught us this. Mass and energy curve this fabric, and the curves tell objects how to move. It's like placing a heavy ball on a stretched rubber sheet. The sheet bends beneath it, creating a valley. Roll a marble nearby, and it curves inward, following the slope. That's gravity, not a force pulling across empty space, but the shape of space itself. Now, imagine placing something so heavy, so compressed on that sheet, that it creates not just a valley, but a pit so deep it's nearly vertical, a well from which nothing can climb out, not even light, which moves as fast as anything can move in this universe. That's a black hole. And at the edge of this pit, there's a boundary. We call it the event horizon. It's not a physical surface. You couldn't touch it or stand on it. There's no shell, no membrane, no wall. It's simply the point of no return. The place where if you cross it, every possible path leads inward. Even if you pointed yourself straight up and traveled at the speed of light, you would still fall toward the center. From outside, the event horizon appears as a perfect dark sphere, perfectly black because no light escapes to tell you what's within, perfectly smooth because black holes, in a way, are simple. They have mass, they may spin, they may carry electric charge, but beyond that, they have no features, no mountains or valleys on their surface, no continents or clouds, just a boundary between inside and out. But here's something strange and wonderful about this boundary. It's not the same for everyone. Imagine you're floating in space near a black hole hovering safely outside the event horizon. You're watching a friend who decides to fall in. You see them drift closer to the boundary, moving steadily toward it. And then something odd begins to happen. From your perspective, they start to slow down. Their movements become sluggish. Their signals arrive more slowly. The light from them becomes stretched, shifting toward red. As they approach the horizon, they seem to move slower and slower, dimmer and dimmer, and you never quite see them cross. From your point of view, they appear frozen at the edge, approaching the boundary forever, but never reaching it. Time for them seems to stretch toward infinity. But from your friend's perspective, nothing strange happens at all. They don't feel any barrier. They don't sense any change. They simply float smoothly through the horizon in what feels like ordinary time. Their watch ticks normally. Their heart beats at its usual rhythm. They cross the event horizon and continue falling inward. Two perspectives, both true, both real. This is what gravity does to time. Near massive objects, time slows down, not metaphorically, not as a trick of perception. Time actually genuinely passes more slowly where gravity is stronger. Right now, even here on Earth, your feet experience time slightly differently than your head. The difference is tiny, impossibly small to notice, but it's real. GPS satellites orbiting above us must account for this effect. Time ticks faster for them up in orbit than it does down here on the surface. Without corrections for this gravitational time dilation, your phone's navigation would drift off by kilometers each day. Near a black hole, this effect becomes extreme. Hover just outside the event horizon, and time crawls for you while racing ahead in the rest of the universe. Minutes for you could be years, centuries, eons outside. You could watch stars live and die, watch galaxies spin like pinwheels, all while barely aging yourself. And inside the horizon, something even stranger occurs. The roles of space and time shift in a way. Outside, you can move freely through space left or right, forward or back, but you can only move forward through time. Inside, you can no more avoid falling toward the center than you can avoid moving into the future. The singularity at the center becomes not just a place, but an event in your future. Inevitable. What is this singularity? It's the final mystery at the heart of every black hole. Our equations tell us that all the mass, everything that has fallen in, gets compressed into a point of zero volume, infinite density, infinite curvature of space. But that word infinite is physics' way of admitting defeat. It means our mathematics has reached its limit. General relativity. Einstein's beautiful theory of gravity breaks down at the singularity. It cannot tell us what happens there. And quantum mechanics, our equally beautiful theory of the very small, should matter at this scale, but we don't yet know how to combine it properly with gravity. What truly exists at the center of a black hole, we cannot say. And perhaps that's as it should be. Perhaps the universe is allowed to keep some secrets. The singularity is hidden behind the event horizon, veiled from view, forever beyond our ability to observe directly. We call this cosmic censorship, the idea that nature hides its singularities from us, keeps them wrapped up where we cannot see them. It's almost modest of the universe, isn't it? But we can be at peace with not knowing. We don't need to understand everything to appreciate the beauty of black holes, to sense their strangeness, to recognize what they teach us about reality. Because black holes show us that space is not empty backdrop. It has shape. It can curve. It can flow. They show us that time is not absolute. It bends near mass. It slows in deep gravity. It flows at different rates in different places. They show us the limits of knowledge, the boundaries where physics becomes uncertain, where questions outpace answers. And they remind us that endings are not empty, that death, even the death of a star, can give birth to something profound. Right now, as you breathe slowly, there may be millions of black holes in our galaxy alone. They drift silently between the stars. They orbit in pairs. Some are small, just a few times the sun's mass. Others are enormous, millions or billions of times heavier, sitting at the centers of galaxies. Our own galaxy, the Milky Way, has one at its heart. We call it Sagittarius A star. It weighs about 4 million times as much as our Sun, and it's been there, anchoring the center of our spiral for billions of years. We cannot see it directly, but we can watch stars orbiting around it, whipping around this invisible center at incredible speeds. From their motion, we know something massive sits there, something that doesn't shine, something with gravity strong enough to fling stars around like leaves in wind. A black hole. In 2019, scientists captured the first image of a black hole's shadow, not our own, but one much farther away in a galaxy called M87. The image shows a glowing ring of hot gas surrounding a dark center. That darkness is the black hole itself, its silhouette against the light behind it. The image took years to create, required telescopes across the entire Earth working together, and what they saw matched perfectly what Einstein's equations predicted over a century ago. Black holes are real, not speculation, not science fiction. They exist. But despite their fearsome reputation, black holes are not violent by nature. They don't roam through space consuming everything. They don't hunt. They don't reach out with tentacles of gravity to snatch passing ships. If our sun were suddenly replaced by a black hole of the same mass, Earth would keep orbiting just as it does now, just colder, just darker. But the orbit would not change, because gravity depends on mass and distance. A black hole has gravity? Yes, but so does any object with mass. From far away, the gravity of a black hole is no different than the gravity of a star of the same mass. It's only when you get very close that things become strange, and most things in the universe stay far away. Sometimes a black hole and a normal star orbit each other as a binary pair. The star shines. The black hole is dark, but matter from the star can stream toward the black hole, spiraling inward in a disk. This matter heats up from friction as it falls. It gets so hot it glows in X-rays. These X-ray binaries are some of the brightest sources in the X-ray sky. That's how we find many black holes, not by seeing them, but by seeing what they do to the light and matter around them. Black holes are patient. They don't chase. They wait. They persist. They exist in quiet darkness, bending space around them, slowing time near them, keeping their secrets. And they are not truly eternal. In 1974, Stephen Hawking discovered something remarkable. Black holes can radiate. Very slowly, very faintly, quantum effects near the horizon allow them to emit particles and energy. This Hawking radiation is incredibly weak, far too faint to detect from any real black hole. But over unimaginably long timescales, trillions upon trillions of years, far longer than the current age of the universe, this radiation would cause a black hole to slowly evaporate, to give its mass back to the cosmos, bit by bit, until eventually nothing remains. Nothing lasts forever. Not stars, not planets, not even black holes. But for now tonight, they are here, quiet and dark and strange, teaching us about the nature of space and time, showing us where physics reaches its limits, reminding us that the universe is deeper and stranger than everyday experience suggests. And sometimes, in the vastness of space, two black holes find each other, not by accident, not by chance, but drawn together by the mathematics of gravity, by the curvature they create in space. Their gravitational fields overlap. They begin to orbit, and a dance begins, a slow spiral that can last for millions of years. Two invisible partners circling in the dark, drawing closer with each orbit, sending out ripples in space as they move. And when they finally merge, when their event horizons touch and they become one, they send out a signal unlike anything else in the universe. Not light, not sound, but waves in the fabric of space itself. We'll come to those waves soon, but for now, rest in this knowing. Black holes exist. They are born from the deaths of massive stars. They are shaped by gravity's mathematics. They are both ending and beginning, and they raise a question that goes deeper than physics. Because if two black holes can meet, if they can circle and spiral and merge, then we must ask something fundamental. What does it mean for two things to become one? When black holes merge, do they lose their separate identities? Is the result simply the sum of two, or something new entirely? To answer that, we need to think about identity itself, about boundaries, about what makes something one thing rather than two. Because before we ask whether two black holes can merge, perhaps we should ask whether they were ever truly separate at all. Let's drift into that question next, into the problem of boundaries, of separation of what we mean when we say two or one. Close your eyes. Breathe slowly. The journey continues. Because before we ask whether two black holes can merge, perhaps we should ask whether they were ever truly separate at all. And that question, quiet as it is, opens something deeper. Because when we look closely at what makes two black holes two, we find that the answer is not as simple as we thought. Let's drift into that mystery now. What makes two black holes two? It sounds like an odd question, almost philosophical, but it's also deeply physical. Because if we want to know whether two black holes can become one, we first need to understand what we mean by two, what separates them, what makes each one distinct, and the answer reveals something beautiful and strange about the nature of reality itself. Imagine you're floating in space looking at two black holes far apart. One is here, one is there. They each have their own event horizon, their own region of no return. Mass here, mass there. Two separate objects. Or are they? Let's think about what defines a black hole. We said earlier that black holes are simple. They have mass, they may have spin, they may have electric charge. That's it. 3 numbers, nothing else. No color, no texture, no hidden features. This is called the no-hair theorem, a playful name for a profound idea. It says that black holes have no hair, no distinguishing characteristics beyond those 3 properties. Everything else, all the complexity of the star that formed them, all the details of how they were born gets erased. 2 black holes with the same mass, same spin, same charge are identical, completely indistinguishable. So if you have 2 such black holes separated in space, what makes them 2 rather than 1? The answer seems obvious at first. They're in different places. They have separate event horizons. There's space between them. They are 2 distinct regions of curved space-time. Simple enough. But let's look more closely. Each black hole creates a gravitational field around it. This field extends outward in all directions, getting weaker with distance, but never quite reaching zero. Gravity has infinite range. In principle, every mass in the universe affects every other mass, no matter how far apart. So, the 2 black holes, even when separated by vast distances, are not truly independent. Their gravitational fields overlap. They influence each other, however faintly. The presence of one changes ever so slightly the space-time around the other. Where does one black hole's influence end? and the others begin. There's no clear boundary, no line you could draw in space that separates their effects cleanly. From far away, their combined gravitational field looks like a single source. The distinction between two becomes a matter of perspective, of scale of how close you look. This is not just true for black holes. It's true for everything. Your body affects the moon with your gravity. The effect is tiny, impossibly small, but it's real. The moon's gravity affects you. You and the moon are separate objects, yes, but your gravitational fields overlap. You're connected through the fabric of space. Where do you end and the world begins? The question becomes less clear the more you think about it. You breathe in air. That air becomes part of you, oxygen entering your blood, becoming the fuel your cells burn. You breathe out. Carbon dioxide leaves your body and becomes part of the air again. When exactly did the air stop being outside and become you? When did it stop being you and become outside again? There's no precise moment, no exact boundary. The transition is smooth, continuous, a matter of perspective and definition rather than hard physical separation. This is true at every level. Your body exchanges atoms with the environment constantly. Skin cells fall away. New ones form from food you eat. The atoms that made you a year ago are not the same atoms that make you now. Are you still the same person? Are you continuous across time? Even though your physical substance changes, philosophers have puzzled over this for centuries. The ship of Theseus paradox asks, if you replace every plank of a ship one by one until no original piece remains, is it still the same ship? There's no obvious answer. Black holes face a similar question, not about time, but about space. If two black holes are connected through their overlapping gravitational fields, if their effects on space-time blend together, are they truly separate? And if they're not truly separate, what does it mean for them to merge? Let's think about the mathematics for a moment, not with equations, but with ideas. Einstein's equations describe how mass curves space-time. For a single black hole sitting alone in empty space, the solution is elegant. It's called the Schwarzschild solution, after Karl Schwarzschild, who found it just months after Einstein published his theory. This solution describes the curved geometry around a single, non-rotating black hole. It's perfectly spherical, perfectly simple. For two black holes, things become more complicated. You cannot simply add two Schwarzschild solutions together and get the right answer. Gravity doesn't combine that way. The curvature created by one mass affects how you measure and describe the curvature from another. Instead, you have to solve Einstein's equations for both masses together, treating them as a single system. And when you do that, what you find is remarkable. From a mathematical perspective, two black holes orbiting each other are described by a single solution to Einstein's equations. Not two separate solutions that happen to coexist, but one unified description of curved spacetime. The distinction between two black holes and one system becomes a matter of interpretation. Yes, there are two event horizons, two separate regions from which nothing escapes, but they exist within a single unified gravitational field. They are like two whirlpools in the same stream, distinct features, but part of one flow. Now, let's talk about the event horizon itself, because it reveals something even stranger about boundaries. We said earlier that the event horizon is not a physical surface. It's a mathematical boundary, the point of no return. But here's something most people don't realize. The event horizon is not the same for all observers. Imagine you're falling into a black hole. From your perspective, you cross the horizon smoothly. Nothing special happens at that moment. No barrier, no sensation, no change you can feel. You simply pass from outside to inside. But to someone watching you from far away, hovering safely outside, you never quite cross. They see you approach the horizon, slow down, freeze. Your image gets dimmer and redder, but never quite vanishes past the edge. From their perspective, you remain outside, suspended forever at the boundary. Two descriptions, both mathematically valid, both correct from their own frame of reference. So, is the horizon real or not? The answer is that real becomes a complicated word. The horizon is a feature of space-time, but it's also observer-dependent. It exists but differently for different observers. This is what physicists call complementarity. Two apparently contradictory descriptions can both be true, describing the same reality from different perspectives. It's similar to how time itself works in relativity. There's no universal now that everyone agrees on. Your present moment is different from someone else's if you're moving at different speeds or experiencing different gravity. And yet, we don't say time is an illusion. We say time is relative, observer-dependent, but still real. Boundaries work the same way. The edge between you and not you, between inside a black hole and outside between two objects, and these boundaries are real in the sense that they have physical consequences, but they're also fuzzy, relative dependent on how you look at them. Eastern philosophy has explored this idea for millennia. Buddhism teaches the concept of anatta or non-self, the idea that there is no fixed, permanent essence that makes you you. Instead, you are a collection of changing processes, a temporary pattern in the flow of existence. You think of yourself as a distinct individual, separate from the world. But look closely, and the boundaries blur. Where do you end at your skin? But your skin is constantly shedding and renewing in your body, but the atoms in your body are constantly being replaced. The Buddhist answer is that you is a useful concept, but ultimately a convention, not a fundamental truth. The self is empty of inherent existence. It exists in relation to other things, defined by context and perspective, not by some core essence that remains unchanged. Black holes are similar. A black hole is defined by its event horizon, by the boundary between trapped and free. But that boundary is observer-dependent. The black hole's selfhood is relational, not absolute. And when two black holes orbit each other, their two-ness becomes even more questionable. As they circle closer, their gravitational fields merge more completely. From far away, you see one gravitational source, not two. The space-time around them becomes a unified, curved geometry. The two event horizons remain distinct, yes, but they're like two valleys in the same mountain range, separate, but part of one topography. There's a beautiful term in Buddhist philosophy, interbeing. Thich Nhat Hanh, the Vietnamese Zen master, used this word to describe how nothing exists independently. Everything is made of non-self elements. Look at a flower. You see sun in it, because without sun, it couldn't grow. You see rain soil. Time the gardener's care. The flower is made of non-flower elements. It interis with everything around it. Where does the flower end and the not flower begin? The question has no precise answer. Black holes inter-are with the space-time around them, with the gravitational field they create with each other when they're close enough. And this brings us to something even more fundamental. What is space itself? What is this fabric that black holes curve, that connects them even across vast distances? We've been using the metaphor of a fabric, a stretched sheet. But what is it really? Space is not a thing exactly. It's more like a relationship, a way of describing how far apart events are, how objects are positioned relative to each other. Einstein taught us that space and time are woven together into space-time, a four-dimensional geometry that can curve and ripple and flow. But quantum mechanics suggests something even stranger. At the smallest scales, space may not be smooth at all. It might be granular, made of discrete bits, fluctuating and foaming. What we perceive as smooth, continuous space might be an averaged out large-scale view of something much more chaotic underneath. And there's growing evidence that space itself might be emergent, not fundamental, but arising from something deeper, from quantum entanglement, perhaps from information, from relationships between parts of a system. If this is true, then space is not the stage on which physics happens. Space is created by the relationships between things. And if space is created by relationships, then separation itself is a kind of illusion. Two black holes separated in space are not fundamentally separate. They are two features of one relational structure, two patterns in one quantum field, two peaks in one gravitational landscape. The physicist John Wheeler, one of the pioneers of black hole physics, had a saying, mass without mass, charge without charge field without field. He meant that what we call mass or charge or field might not be fundamental properties. They might be geometric features, patterns in space-time itself. A black hole is not a thing with mass. It's a region where space-time has curved in a particular way. The mass is just our way of measuring that curvature. If this is right, then asking, what are two black holes made of, is like asking, what are two whirlpools made of? The answer is water, yes. But more deeply, they're both made of motion, of pattern, of flowing structure. Two whirlpools in a river are distinct. You can point to each one, but they're not separate from the river. They're features of it, temporary patterns in one flow. And if you watch two whirlpools drift toward each other, their edges blur, their flows intertwine, and eventually they merge into one larger swirl. Were they ever truly two, yes and no? They were distinguishable, separate in space, and describable independently. But they were also always part of one river, one body of water, one system. Black holes are patterns in space-time, the way whirlpools are patterns in water. And this raises our deepest question yet. When two black holes merge, when their event horizons touch and become one, what happens to their individual identities? Does something get lost? Does something new emerge? Or was the distinction between them conventional, all along useful, but not ultimate? To answer that, we need to watch what actually happens when two black holes come together. We need to see the physics of the merger itself, the spiral, the collision, the waves that ripple outward. We need to understand how gravity behaves when it becomes extreme, when space-time curves so sharply that it rings like a bell. But before we get there, just rest for a moment with this idea. Boundaries are real but fuzzy. Separation is meaningful, but not absolute. Two things can be distinct and also unified, separate and also one. It's not a contradiction. It's a deeper truth about the nature of reality. You are separate from the person next to you, yes, but you share the same air, the same atoms cycle between you, the same laws of physics govern you both. You are connected through gravity, through light, through the quantum fields that fill all space. You are distinct. You are also one. Both are true. And as you lie here breathing, slowly feel how your breath connects you to the room, to the atmosphere, to the trees that made the oxygen, to the sun that powered the trees. You are not a separate island. You are a pattern in a larger flow. Just like black holes. Two black holes orbit each other in the dark. They are separate, yes. Two event horizons, two centers, two distinct objects in space. But their gravitational fields overlap. Their futures are entangled. Their geometry is unified. They are two. They are also one system. And as they spiral closer, as the dance tightens and time dilates and space curves more and more steeply, the question of their two-ness becomes less and less meaningful, until finally, inevitably, they touch. And what was two becomes one, not by destruction, but by transformation, not by losing identity, but by transcending it. Let's watch that transformation now. Let's see what happens in the final moments before merger, when gravity becomes so strong that space-time itself trembles. Close your eyes. Breathe gently. The spiral is beginning. There are no voices in space. No sound carries across the vacuum between stars. No wind rustles. No echo returns. And yet the universe speaks. It speaks through gravity, through motion, through the trembling of space-time itself. And when two black holes orbit each other, when they spiral closer in their long patient dance, they send out a message, not in light, not in particles, but in ripples, gravitational waves. Imagine space-time as a vast, invisible ocean. Most days it's calm, smooth, barely moving. But when something massive accelerates, when stars collapse, or black holes spin, or two of them circle each other, they disturb this ocean. They send out waves that spread in all directions, traveling at the speed of light. These are not waves in space. They are waves of space itself. As a gravitational wave passes through a region, it stretches space in one direction and compresses it in another. Then the pattern reverses. Stretch, compress, stretch, compress. The wave moves through carrying energy and information about whatever created it. Right now, as you lie, still gravitational waves are passing through you. They come from events that happened long ago, from black holes that merged when the universe was younger, from neutron stars that collided billions of light years away. These waves travel through galaxies, through clouds of gas, through planets and stars. Through you, as they pass, they change the distance between things very slightly. Your body stretches by less than the width of an atomic nucleus in one direction, then compresses, then returns to normal. You don't feel it. Your nerves cannot detect such a small change. But it happens. The wave moves through you, like you're not even there, barely noticing your presence. Gravitational waves are how black holes speak to each other and to us. Because black holes themselves don't emit light once they've formed. They don't shine or glow. They're invisible, defined only by their absence, by the light they don't let escape, but they move. And in their motion, They shake space-time. Einstein predicted these waves in 1916, shortly after finishing his theory of general relativity. The mathematics was clear. If mass tells space-time how to curve, and curved space-time tells mass how to move, then when mass accelerates, it should create ripples in the curvature that propagate outward, just as accelerating electric charges create electromagnetic waves, light. But Einstein himself doubted we'd ever detect gravitational waves. They seemed too weak, too subtle. He thought they might remain forever, a mathematical prediction true, in theory, but invisible in practice. He was wrong, but it took a century to prove it. Gravitational waves are extraordinarily faint by the time they reach Earth. Even from the most violent cosmic events, the stretching and compressing of space is incredibly tiny, less than 1 part in a billion trillion. Detecting them requires instruments of almost unimaginable sensitivity. LIGO, the Laser Interferometer Gravitational Wave Observatory, consists of 2 facilities, one in Hanford, Washington, one in Livingston, Louisiana. Each has 2 arms extending 4 kilometers in opposite directions, forming an L shape. Inside each arm, a laser beam bounces back and forth between mirrors. The beams travel up and down their respective arms, thousands of times, then recombine. When the arms are exactly the same length, the 2 beams interfere with each other in a predictable way. But when a gravitational wave passes through it, stretches one arm slightly while compressing the other, the laser beams notice this difference, and the interference pattern changes. That change, impossibly small, tells us a gravitational wave has passed through. How small LIGO can detect a change in length of about 1/10,000th the diameter of a proton. Imagine measuring the distance from Earth to the nearest star and noticing if it changed by the width of a human hair. That's the level of precision required. The instruments must be isolated from every imaginable disturbance. Earthquakes thousands of miles away can shake them. Trucks driving on nearby roads, ocean waves on distant shores, even the thermal jittering of atoms in the mirrors themselves. The mirrors hang from elaborate suspension systems to isolate them from ground vibrations. The entire apparatus sits in vacuum chambers to eliminate air turbulence. Laser systems of exquisite stability keep the light beams pure. And then the detectors listen, patiently, constantly, waiting for space-time to shiver. On September 14th, 2015, both detectors, nearly 2,000 miles apart, recorded the same signal within milliseconds of each other. A chirp, a rising frequency lasting a fraction of a second. The pattern matched precisely what Einstein's equations predicted for 2 black holes spiraling together and merging. The wave had traveled for 3 billion years, carrying the story of 2 black holes that lived and died long before Earth had animals or plants or even complex cells. And their final embrace sent out this ripple that traveled across 1 billion years to arrive at Earth on that September morning. We heard it, or rather, we felt it. We detected the trembling of space. For the first time, humanity didn't just see the universe. We felt it move beneath us. Since that first detection, we've heard dozens more. Black holes of various sizes, some spinning rapidly, others slowly, merging at different distances in different configurations. Each creates its own signature, its own pattern in the ripples of space-time. More detectors have joined the search. Virgo in Italy, Kagra in Japan, Together, they form a network triangulating the sources of gravitational waves, pinpointing where in the sky these mergers occur. And future detectors will listen to even more. LISA, a space-based observatory planned for the 2030s, will have arms millions of kilometers long, orbiting the sun, detecting waves from supermassive black holes at the centers of distant galaxies. We're building a new way of experiencing the cosmos, not through light, but through gravity's motion. But what creates these waves? What makes space-time ripple when black holes orbit? Let's watch more closely. Two black holes separated by vast distances at first orbit each other. They may have been doing this for millions of years, perhaps billions. Each curves space-time around itself, and those curves overlap, creating a combined gravitational field. They circle, slowly bound by mutual gravity, and with each orbit, they send out gravitational waves. These waves carry energy. Not much at first when the black holes are far apart and moving slowly, but the energy has to come from somewhere, and it comes from the orbital motion itself. As the black holes radiate gravitational waves, they lose orbital energy, and when they lose energy, their orbit shrinks. They drift closer together. This is the key. The spiral is powered by energy loss. At first, the process is extraordinarily slow. When the black holes are many times their own size apart, the waves they emit are weak. The orbit might shrink by mere centimeters per year, less than your fingernails grow. But over millions of years, it adds up. The orbit tightens. The black holes move faster as they get closer, and as they move faster, they emit stronger waves. More energy radiates away. The orbit shrinks more quickly. It's a feedback loop, gentle at first, but gradually accelerating. Imagine water spiraling down a drain. Far from the center, it moves slowly, almost imperceptibly, but closer in it, speeds up. The spiral tightens. The flow accelerates. For black holes, this process can take eons. Two black holes might orbit for 1 billion years, gradually drawing together, wave after wave, carrying energy into space. The universe is patient. Gravity is patient. There's no hurry, but eventually they enter what astronomers call the inspiral phase. Now, the process becomes faster, more dramatic. The orbit shrinks measurably. The waves grow stronger, their frequency increasing. If you could translate the gravitational waves into sound waves, you'd hear the pitch rising steadily, a cosmic crescendo building over thousands of years. When the black holes finally get close enough, their waves enter the frequency range that LIGO can detect. Now we can hear them. For the last few minutes before merger, their spiral becomes audible to our instruments. The signal strengthens. The frequency climbs higher. The black holes orbit faster and faster. In the final seconds, they may be orbiting each other hundreds of times per second. Their event horizons now, just a few times their own diameter apart, whip around at tremendous speeds, perhaps half the speed of light or more. This is not gentle. This is extreme. The gravitational field around them is immensely strong. Time flows very differently near them than it does far away. Space is curved so steeply that light paths twist and bend in complex ways, and the energy radiated in gravitational waves becomes enormous in those final moments before merger. The power output in gravitational waves can exceed the combined light output of every star in the observable universe. more power than hundreds of billions of galaxies shining together. But you wouldn't see it, not with your eyes, not with any telescope that detects light, because the energy doesn't come out as photons, as particles of light. It comes out as geometry, as ripples in the structure of space-time itself. The fabric of reality trembles with the force of their motion. Scientists use supercomputers to model this process, to solve Einstein's equations for these extreme conditions. The calculations are immensely complex. You cannot use shortcuts or approximations. You need the full machinery of general relativity. The simulations show something beautiful. The spiraling black holes create a pattern. In space-time, a rotating pulsing distortion that sends waves outward in a characteristic pattern. When LIGO detects a signal, scientists compare it against these simulations. They search through vast libraries of predicted waveforms, looking for the best match. From that match, they can determine the masses of the two black holes, how fast they were spinning, how far away the merger occurred, all from a signal lasting less than a second. The agreement between theory and observation is stunning. Einstein's century-old equations predict exactly what modern detectors observe. But let's return to the black holes themselves. In those final moments, the black holes are close now, very close. Their event horizons are separated by only a few times their own diameter. They orbit each other many times per second. At these speeds, relativity dominates everything. Each black hole drags space-time around itself as it spins and moves. This effect, called frame dragging, means that space itself is rotating near the black holes. Anything nearby gets swept along with that rotation, like a boat caught in a whirlpool. Time near the black holes flows strangely. An observer hovering nearby would experience time more slowly than someone far away. The gravitational time dilation is significant now. Minutes there might be hours or days elsewhere. But the black holes themselves, falling freely through curved space-time, don't experience anything unusual. They simply follow the geometry created by their combined mass. That geometry is no longer simple. It's not two separate wells in space-time. It's a single, unified, dynamically changing field of curvature. Space warps. Time bends. The two effects intertwine in ways that are difficult even for physicists to visualize. Light traveling near the black holes follows bizarre paths. It can spiral around one or both before escaping. It can be gravitationally lensed, bent and focused like light through a warped lens. If you could watch from a safe distance with powerful instruments, you might see multiple distorted images of the same distant stars, light bent around both black holes in different paths. But mostly, you'd see darkness. Two black regions, circular, perfectly dark, circling each other, faster and faster. And you'd feel, if your instruments were sensitive enough, the pulsing of gravitational waves, growing stronger with each passing moment. The final orbits happen quickly once they begin. After millions or billions of years of slow spiral, the end comes in seconds. The black holes whip around each other. The frequency of their orbit climbs higher. The gravitational waves they emit become a torrent. Space around them is not just curved, it's violently distorted, stretched and compressed in rapid oscillation. The geometry itself is dynamic, changing faster than light could cross from one black hole to the other. This is called the strong field regime, where gravity is so intense that all the nonlinear effects in Einstein's equations become important, where space-time behaves in ways that have no analogy in everyday experience. And then after all this time, after all this spiraling, they approach the moment of merger. Their event horizons draw close. The space between them becomes less and less. The orbital frequency reaches its maximum. And in the next instant, something remarkable happens. But before we watch that final moment, just pause here. Feel the anticipation. Two ancient objects born from the deaths of massive stars billions of years ago have found each other across the vastness of space. They've circled for eons. They've radiated their energy into the fabric of the universe. And now they're about to become one. Not through violence exactly, not through collision in the usual sense, but through a transformation so complete that what emerges is entirely new. Let's breathe here for a moment. Let your mind rest. The mathematics is complex, but the idea is simple. Two things long separate are about to unite, and in their union, they'll send out the strongest gravitational waves they've ever produced. A final shout into the cosmos, a signal that will travel for billions of years, carrying the news of this moment to distant galaxies we'll never see. The merger is coming. Let's watch it unfold. Their event horizons touch. This is not like two objects colliding. There's no impact, no crash, no sound. The horizons are not physical surfaces. They're boundaries in space-time, where the geometry becomes so extreme that even light cannot escape. When they touch, the topology of space-time changes. Imagine two separate spheres. Each is its own closed surface. Now, imagine them joining. The moment they connect, they're no longer two spheres. They become a single connected surface, like two soap bubbles merging into one. But this happens not in ordinary space, but in the geometry of space-time itself. The mathematics describes this as a topology change. The number of disconnected components goes from 2 to 1, instantly, in less than a millisecond. During this brief moment, the shape of the new horizon is not spherical. It's distorted, elongated. Some physicists describe it as looking like a dumbbell or a peanut. Two bulges connected by a narrow bridge. This shape is unstable. It cannot last. The event horizon, once merged, must settle into the simplest stable configuration, a rotating sphere, the Kerr solution, the final state that all rotating black holes eventually reach. But getting there takes time, fractions of a second, and during that time, the distorted horizon oscillates. It vibrates, and those vibrations release energy, gravitational waves. The final burst, about 3 to 5% of the total mass energy of both black holes, is converted into gravitational waves in this final moment. 3 to 5% might not sound like much, but remember, we're talking about the mass of millions or billions of suns. The amount of energy released in this brief instant exceeds the combined light output of all the stars in the observable universe. For a fraction of a second, this merger is the brightest gravitational event in the universe, brighter than supernovae, brighter than gamma ray bursts, brighter than anything except perhaps the Big Bang itself. But bright here means gravitational brightness. There's no light, no electromagnetic radiation at all, unless there happens to be gas or matter falling in at the same time, which is rare. Just pure gravitational waves. Ripples in space-time itself, spreading outward at the speed of light, carrying energy, carrying information about what just happened. The waveform at this moment is called the merger signal. It's distinct from the earlier in spiral. The frequency has reached its maximum. The amplitude is at its peak, and then suddenly it begins to change character. The clean rising chirp of the inspiral gives way to something more complex, multiple frequencies rapidly evolving, the sound of space-time itself, ringing and settling. If you could be there impossibly close, yet somehow surviving, you wouldn't see much. Two regions of perfect darkness, becoming one larger region of perfect darkness. The stars behind them would be lensed and distorted in strange, shifting patterns. But you would feel something. If your body could survive the tidal forces, you would feel the gravitational waves passing through you. Your body would stretch and compress in a pattern that changes moment by moment. Of course, you couldn't actually be there. The tidal forces would tear apart anything made of atoms long before you got close enough to notice. This is a thought experiment, a way of imagining the unimaginable. But LIGO can be there in a sense. LIGO's instruments safe on Earth, billions of light years away, can detect these waves. The merger signal, when it arrives, lasts only fractions of a second, a sharp peak in the detector output, and then the beginning of something new, the ring down. What has emerged from this merger? A single black hole, larger than either of its parents, spinning because both orbital and spin angular momentum are conserved. Hot in a sense because it's distorted and vibrating, but the distortions won't last. The vibrations will fade, and what will remain is the simplest, most elegant solution to Einstein's equations, the Kerr black hole, defined completely by just two numbers, mass and spin. Everything else is gone. All the complexity of the two parent black holes, all their individual histories, all the details of their approach and merger, all of it has been radiated away or hidden behind the event horizon. The no-hair theorem is satisfied once again. A black hole has no features, no individuality, no memory, except what's encoded in mass, spin, and charge. Or does it? The question of what information remains, how the past is encoded in the present, is still not fully answered, but we'll return to that question later. For now, just observe. Two have become one, not through addition, but through transformation. What exists now is not the sum of what existed before, but something genuinely new, a synthesis, as Hegel would say, a new being that contains both parents, but is neither of them, something that has emerged from the destruction of separation, and the universe has witnessed it. The gravitational waves carry the story outward. Anyone with the right instruments, anywhere in the universe, can receive that signal and know here at this time, in this place, two black holes merged into one. The event is written into the structure of space-time itself, permanent, irrevocable, a fact that will propagate forever outward at the speed of light, reaching new parts of the universe for billions of years to come. Every profound transformation is violent in some sense, not necessarily violent in the way we usually mean with harm or destruction, but violent in that it involves the complete breaking down of what was before. Birth is violent, the tearing away from the womb, the sudden exposure to light and air and separation. The first breath is a shock to the system, a traumatic change from one mode of existence to another. Death is violent, the cessation of heartbeat, of breath, of the integrated functioning that defines a living organism. A boundary is crossed. What was alive is no longer alive. And transformation, real transformation, not just superficial change, is perhaps the most violent of all. Because in true transformation, you cannot remain who you were. The old self must dissolve. The old boundaries must break down. The comfortable definitions must be released. This is why transformation is so often resisted, not because people don't want to grow, but because growth requires a kind of death, the death of the old self, the death of the familiar, the death of the known. The mystic traditions understand this. They speak of ego death, of the dark night of the soul, of the dissolution that must precede enlightenment. Rumi writes, "You must die before you die, so that when you die, you do not die." The ego, the sense of being a separate bounded self, must be dismantled, not destroyed in the sense of annihilation, but transformed, seen through, recognized as a construct rather than a fundamental truth. This process is described as violent because it feels violent. It feels like dying, and in a sense it is. The person you thought you were cannot survive the realization of what you actually are. The black hole merger illustrates this perfectly. The two black holes don't simply come together and remain two distinct entities within a larger whole. They cease to exist as separate entities entirely. Their individual event horizons merge and disappear. A new horizon forms. A new identity emerges. There's no going back. You cannot unmerge black holes. The topology change is irreversible. What was two is now one permanently. In human life, we experience smaller versions of this all the time. Every major life transition involves a kind of death and rebirth. When you fall deeply in love, the person you were before, the one who was complete and sufficient alone, must die. A new self emerges, one defined partly by relationship, by connection, by the presence of another. When you become a parent, your old self dies. The person who was free to act only for themselves, who could take risks without considering another life, who could sleep through the night, that person is gone. A new self emerges with new priorities, new fears, new capacities for love and worry. When you experience profound loss, part of you dies with what you've lost. The self that included that relationship, that future, that hope, it dissolves. And eventually, if the grief is processed, rather than suppressed, a new self emerges, changed, larger in some ways, smaller in others, but fundamentally different. This is not comfortable. We want to grow without changing. We want to gain without losing. We want synthesis without the dissolution of thesis and antithesis. But it doesn't work that way. Real change, deep transformation, requires letting go of the old form completely, not just modifying it, not just adding to it, but releasing it. The violence is in the resistance. When we cling to the old form, even as it's dissolving, we create suffering. When we accept the dissolution, allow it, even embrace it, the violence becomes something else. It becomes power, creative power, the power of transformation itself. In these final moments, before merger, something strange happens to time. We've talked about gravitational time dilation, how time flows more slowly in strong gravitational fields. But near merging black holes, the effect becomes so extreme that our usual concept of time begins to break down. From far away, watching through a telescope, you'd never actually see the merger happen. The light or gravitational waves from points closer and closer to the event horizons takes longer and longer to reach you. Time appears to slow down asymptotically. The final moment seems to recede forever into the future. But for a particle falling into the merging black holes, time flows normally. It crosses the horizon and continues inward. No infinite time, no slowing down, just geometry. Two observers, two descriptions, both correct within their own frame of reference, neither more true than the other. This is the principle of complementarity borrowed from quantum mechanics, but applicable here too. The same event has different descriptions depending on the observer, and there's no absolute observer-independent truth that resolves the difference. What does this mean for time itself? It means that time is not a container, not a stage on which events occur. Time is relational. It's defined by change by process, by the unfolding of one state into another. Einstein showed us that time is relative to motion and gravity. But the deeper truth is that time is relative to observation, to reference frame, to the structure of space-time itself. Near the merger, space-time is so warped that the usual separation of time and space becomes ambiguous. Time-like and space-like directions mix. What looks like a direction in time from one perspective looks partly like a direction in space from another. And inside the merged black hole, beyond the event horizon, the distinction collapses entirely. The radial direction toward the singularity becomes time-like. You can no more avoid moving toward the center than you can avoid moving toward the future. The two become the same thing. This has profound implications. If time is not absolute, if it's observer-dependent and frame-relative, then what about our experience of time? What about the feeling of now, the sense of present moment that seems so immediate and real? Physics suggests that now is not a fundamental feature of reality. Different observers have different nows. There's no universal present moment. What's present for you might be past or future for someone moving differently or located in a different gravitational field. Yet we experience now, vividly, undeniably. The present moment seems like the most real thing there is. Perhaps this is where physics and philosophy must diverge, or at least complement each other. Physics describes time as it appears in mathematical models, as a coordinate, a dimension, a relative quantity. But philosophy points to time as it's lived, as experience, as the flow of consciousness through what Bergson called duration, not measurable quantifiable time, but time as pure becoming. In deep meditation, practitioners report that time can seem to stop, not in the sense of time dilation, but in the sense that the usual feeling of past, present, future dissolves. There's only this moment, eternal and unchanging, even as it includes all change. Is this an illusion? A confusion of subjective experience with objective reality? Or is it perhaps a glimpse of something more fundamental? A direct experience of what lies beneath the construction of time as we usually know it. The black hole merger suggests something in extreme conditions. The structures we rely on, including time, reveal themselves as contingent, relative, observer-dependent. Not false, but not absolutely true either. And if that's true in physics, might it not also be true in consciousness? Might the flow of time we experience be a construction useful, but not ultimate? And might there be a way of experiencing that transcends this construction? The mystics have always said so. Now, physics in its own way seems to agree. Time, like separation, like identity, like all the structures we navigate in ordinary life, these are real in their domain, useful in their context, but not the final truth of what is. The merger is complete, but the new black hole is not yet stable. Imagine striking a bell. The initial impact produces a loud, sharp sound, but that's not the end. The bell continues to ring, producing a clear tone that gradually fades. The merged black hole does something similar. It rings. The distorted, non-spherical shape of the event horizon immediately after merger is unstable. The geometry wants to settle into the simplest stable, form a rotating sphere, the Kerr solution. But it can't get there instantly. The shape must relax, and that relaxation takes time. Fractions of a second, but measurable time nonetheless. During this relaxation, the black hole oscillates. It's alternately oblate and prolate fat and thin, bulging in different directions. These oscillations are called quasi-normal modes. Quasi-normal because they're not quite the normal modes you'd see in a simple oscillating system. They're damped. They decay exponentially with time, and as the black hole oscillates, it radiates. Gravitational waves still, not as strong as during the merger, but with a distinctive character. Each quasi-normal mode has a specific frequency determined entirely by the mass and spin of the final black hole. A heavier black hole rings at a lower frequency. A rapidly spinning black hole has different overtones than a slowly spinning one. This is the ring-down signal. If you convert the gravitational waves into sound, it literally sounds like a tone decaying away. A pitch that depends on the black hole's properties, fading into silence. For LIGO and other gravitational wave detectors, the ring-down is incredibly valuable. By measuring the frequencies of the quasi-normal modes, scientists can determine the mass and spin of the final black hole. They can test whether the result matches what general relativity predicts. So far, every detected merger has shown perfect agreement. The ring-down frequencies are exactly what Einstein's equations say they should be. The final black hole is exactly the Kerr solution, with no deviations, no anomalies. This is remarkable. It means that general relativity works perfectly, even in the most extreme conditions we've ever tested, in regions of space-time curved so intensely that nothing in our everyday experience comes close. The ring-down typically lasts longer than the merger itself. While the merger happens in milliseconds, the ring-down can continue for tens or even hundreds of milliseconds, depending on the mass of the black hole. Larger black holes ring longer at lower frequencies. Smaller black holes ring briefly at higher frequencies. The relationship is precise, predictable, and has been confirmed in every observation. As the ring-down proceeds, the oscillations become smaller and smaller. The gravitational waves become weaker and weaker. Eventually, they fade below the noise level of the detectors and can no longer be measured. But in principle, they continue, exponentially decreasing, approaching zero, but never quite reaching it, asymptotically silent. And when they've faded enough, what remains a single black hole, perfectly spherical, or nearly so, rotating steadily, still, quiet. No more oscillations, no more radiation, except for the incredibly faint Hawking radiation that all black holes emit, and which would take trillions upon trillions of years to evaporate. Even a small black hole, the final state, equilibrium, the end of the process. What began as two objects circling for millions of years, spiraling in over thousands of revolutions, merging in a violent instant and ringing for fractions of a second, has now settled into the simplest possible configuration. Three numbers define it completely: mass, spin, and charge. Everything else is gone. All the details of the merger, all the complexity of the approach, all the history of the two parent black holes erased. The no-hair theorem holds. Black holes have no hair, no distinguishing features beyond those three numbers. Or do they? We still haven't fully resolved the information paradox. We'll address that in the next chapter. But for now, observe what's happened. Two distinct entities have become one. The process was violent, energetic, observable, across billions of light years. It released more power than all the stars in the visible universe. And yet the end result is simple, elegant. Still, every crisis eventually subsides. Every storm passes. Every intense experience, no matter how overwhelming, eventually gives way to calm. This is not the same calm that existed before. It's not a return to the old equilibrium. It's a new equilibrium at a different level, with a different understanding. The black hole after ring down is not the same as either of the black holes before merger. It contains both of them in a sense. Their mass, their angular momentum, their energy, all of it is preserved in the final state. But the final state is simpler than the sum of the initial states. This is what Hegel meant by aufheben, a German word that means simultaneously to cancel, to preserve, and to transcend. The synthesis cancels the separation of thesis and antithesis. It preserves their essential content, and it transcends both in a new unity. In your own life, you've probably experienced this, a period of crisis, of transformation, of upheaval. Everything seems chaotic. The old structures are breaking down. You don't know who you are anymore, or where you're going. And then gradually, or suddenly, things settle. A new pattern emerges. You find your footing again, not where you were before, but somewhere new. The new you contains the old you. The experiences you went through are part of you now, but you're not defined by them. You're not stuck in them. You've integrated them and moved on. This is the ring down in human terms. The oscillations damping out, the system returning to stability, not the old stability, but a new one. And here's something important. You can't rush this process. The black hole rings for exactly as long as its properties dictate. You can't make it settle faster. It follows the mathematics of general relativity with perfect precision. Similarly, healing takes the time it takes. Grief has its own rhythm. Integration happens at its own pace. Trying to force it, trying to move on before you're ready, usually just prolongs the process. There's a difference between suppression and integration. Suppression is pushing the experience away, pretending it didn't happen or didn't matter. That doesn't work. The oscillations continue underneath, creating tension and instability. Integration is allowing the experience to settle into you, feeling it fully, letting it change you, and then naturally finding the new equilibrium that includes and transcends what happened. The ring down is not silent suffering, it's active settling. The black hole is doing something during this time. It's radiating energy, releasing the last traces of the asymmetry from the merger. You too, during periods of integration, are releasing, letting go, radiating outward the energy of the transformation, sometimes through tears, sometimes through words, sometimes through art or work or silence. And gradually you settle. The oscillations dampen, the intensity fades. You find yourself stable again, but at a new level, with new capacities, with new understanding, wiser perhaps, quieter certainly, simpler. In some ways, the complexity of the crisis has resolved into clarity. There's a famous Zen saying about the stages of practice. Before I studied Zen, mountains were mountains, and rivers were rivers. While I studied Zen, mountains were not mountains, and rivers were not rivers. After I studied Zen, mountains are mountains, and rivers are rivers. This describes a journey from naive simplicity through complexity and confusion to a deeper simplicity on the other side. The black hole exemplifies this perfectly. Before merger, two simple objects, each described by just a few parameters. During merger, incredible complexity, non-linear dynamics, multiple frequencies, space-time tearing and reconnecting. No simple description possible. After ring down again, one simple object described by just a few parameters. But the final simplicity is not the same as the initial simplicity. It contains the memory of complexity. It emerges from it. It's simplicity that has passed through and integrated the complex. This is what we might call mature simplicity, or sophisticated simplicity, or enlightened simplicity. It looks simple from the outside. The enlightened person seems ordinary, does ordinary things, chops wood, carries water, as the saying goes. But the ordinariness is transparent now. It's not naive, it's not unconscious, it's simplicity with full awareness. Simplicity that includes and transcends complexity. Many people seek simplicity as an escape from complexity. They want to go back to how things were before they knew too much, before they experienced too much, before they understood how complicated everything is. But you can't go back. The innocence of not knowing, once lost, cannot be recovered. What you can find is the simplicity beyond complexity, the clarity that emerges not from avoiding difficulty, but from moving through it. The black hole shows us this is possible, not just metaphorically, but as a feature of physical law. Complex systems can evolve toward simplicity. Chaos can resolve into order. Many degrees of freedom can reduce to a few, but the reduction is not a loss. It's a refinement. The final simple state contains information about the complex process that produced it. The three parameters of the final black hole mass, spin charge, encode the entire history of the merger in their specific values. Similarly, your simple presence after deep transformation contains your whole history. You don't need to explain it or display it. It's there integrated into who you are now. The wisdom traditions speak of this often. The master who seems ordinary, the sage who lives simply, the enlightened being who has nothing special about them, and yet somehow everything is different. They've passed through complexity and emerged into simplicity, not the simplicity of ignorance, but the simplicity of integration. The black hole, after all the violence and energy of merger, after all the ringing and radiating of ring down, simply exists, rotating in empty space, defined by three numbers: perfect, complete, still. This is the teaching through transformation, through the dissolution of separation, through the violent crucible of merger. Something genuinely new and yet ultimately simple can emerge. Not two, not even one really. Just this, just now, just what is. The black hole has stopped ringing. Silence has returned. But it's not the silence of absence. It's the silence of completion. And in that silence, we can rest. The black hole has settled. The ring down has faded. Silence. A single object now exists where two once orbited. Mass spin charge three numbers that define it completely. Simple, elegant, final. But wait, what about everything that fell in? What about the entire history of both parent black holes? What about every particle, every photon, every bit of information that crossed those event horizons over billions of years? The no-hair theorem says it's all gone, erased. Only three numbers remain. But quantum mechanics says information cannot be destroyed, ever. It must be preserved somehow, somewhere. So, we have a contradiction, one of the deepest puzzles in modern physics. And it's not just an academic question. It touches on something fundamental about reality itself. If information can be destroyed, then the past can truly vanish. History can be erased. What happened becomes in principle unknowable. But if information must be preserved, then where is it? How is it encoded? What does preservation even mean for something that can never be retrieved? This is the information paradox. And understanding it will take us beyond physics into questions about the nature of existence memory and what it means for something to be real. Let's enter this mystery. Let's start with what we mean by information. In physics, information is precise. It's not just facts or data you can look up. Information is the complete specification of a physical state. If you know all the information about a system, you can predict its future and retrodict its past with perfect accuracy, at least in principle. Think of it this way. If you know the exact position and momentum of every particle in a room, you have complete information about that room. Given the laws of physics, you could calculate exactly what will happen next. You could also, in principle, run the equations backward and figure out what happened before. Information in this sense is conserved in classical physics. If you watch a movie of physical processes and someone plays it backward, the backward version still obeys the laws of physics. Time reversible. No information is lost. Quantum mechanics preserves this, but in a more subtle way. The Schrödinger equation, which describes how quantum states evolve, is unitary. That's a mathematical way of saying it preserves information perfectly. The quantum state at any later time contains exactly the same information as the initial state, just rearranged. Even when quantum systems appear to behave randomly, when you measure a particle and get an uncertain result, the information isn't actually lost. It's spread out into the environment, into correlations between the measured system and the measuring device and everything else. This spreading is called decoherence, but the information still exists. If you could track every particle, every interaction, every correlation, you could, in principle, recover it. This is the principle of unitarity. It's one of the foundational principles of quantum mechanics. Information is never destroyed. Now consider a black hole. You throw a book into a black hole. That book contained information, the specific arrangement of every atom, every word, every idea encoded in its pages. The book crosses the event horizon. It's gone from the observable universe. It falls toward the singularity. Eventually, according to classical general relativity, it's crushed to infinite density at the singularity. What happens to the information? Classical general relativity doesn't worry about this. In classical physics, the information just stays inside the black hole forever, hidden behind the horizon, but still existing in some sense. But here's the problem. Black holes aren't eternal. In 1974, Stephen Hawking made a revolutionary discovery. He showed that when you combine quantum mechanics with general relativity, black holes must radiate. Quantum fluctuations near the event horizon can create pairs of particles. Normally, these pairs annihilate immediately, but near a black hole's horizon, one particle can fall in while the other escapes. The escaping particle is real. It carries energy away from the black hole. To an outside observer, the black hole appears to glow with thermal radiation, now called Hawking radiation. This radiation is incredibly faint. For a stellar mass black hole, the temperature is billionths of a degree above absolute zero, far colder than the cosmic microwave background. So in practice, black holes today are absorbing more radiation than they emit. But in principle, in the far future, when the universe has cooled and expanded, black holes will slowly evaporate. They'll radiate away their mass, growing smaller and hotter as they do, until finally they disappear completely in a final burst. And here's the crisis. Hawking showed that the radiation is thermal. It's random. It contains no information about what fell into the black hole. It's like burning a book. You get heat and light, but you can't reconstruct the text from the smoke and ashes. The information seems to be destroyed. But quantum mechanics says information cannot be destroyed. Something has to give. Either quantum mechanics is wrong, or general relativity is wrong, or our understanding of both is incomplete. This is the black hole information paradox. It's been one of the central problems in theoretical physics for 50 years, and it's still not fully resolved. The information paradox isn't just about physics. It's about the nature of time and existence. If information can be destroyed, then the past can truly vanish. What happened can become, in principle, unknowable. History can be erased from reality. This is disturbing. We generally assume the past is fixed. It happened. Even if we don't remember it, even if we can't access it, it's part of the structure of reality. But what does it mean for something to have happened if all evidence of it can be erased? Philosophers have long debated whether the past exists. Presentism is the view that only the present moment exists. The past has ceased to exist. The future doesn't exist yet. Only now is real. Eternalism, by contrast, holds that all times past, present, and future exist equally. They're all part of a four-dimensional space-time block. Our feeling of now is just a feature of our consciousness moving through this block, but the entire history and future is all equally real. Physics, particularly relativity, seems to favor eternalism. If simultaneity is relative, if different observers disagree about what's happening, now then now, can't be a fundamental feature of reality. The block universe where all of space-time exists at once makes more sense. But quantum mechanics complicates this. The act of measurement seems to create definite outcomes, where before there were only probabilities. Does the past become fixed only when observed? Does observation create reality retroactively? The black hole information paradox brings these questions into sharp focus. If information is destroyed, then eternalism seems wrong. The past doesn't fully exist if it can be erased from reality. What happened becomes genuinely unknowable, not just unknown. But if information is preserved, if it must be preserved by the laws of physics, then the past must exist in some form, somewhere, encoded somehow. Henry Bergson, the French philosopher, proposed that the past doesn't vanish, but accumulates. Duration, he called it, the continuous flow, where each moment contains and carries forward all previous moments. Memory in this view isn't just a recording of the past. It's the past itself, living on in the present, shaping and influencing what is now. Perhaps information is like this. It doesn't exist as a static record somewhere. It exists as the continuous influence of the past on the present, cause and effect. The structure of what is now contains everything that led to it. The black hole merger illustrates this perfectly. The final black hole, defined by just 3 numbers, doesn't contain detailed records of its parent black holes. But those 3 numbers are what they are because of the specific merger that occurred. The mass is the sum of the parent masses minus the radiated energy. The spin is determined by the combination of the parent spins and the orbital angular momentum. Every detail of the merger process influenced these final values. In that sense, the information is preserved, not as a recoverable record, but as the specific reality of what exists now. Is that enough? Does that solve the paradox? Not quite, because quantum mechanics demands more than this. It demands that information be recoverable, at least in principle, that the final state contains enough information to reconstruct the initial state. And it's not clear that a black hole's 3 parameters contain enough information to reconstruct the vast complexity of everything that fell in. So, the puzzle remains. Let's look at one of the most promising solutions. In the early 1990s, Gerard 't Hooft and Leonard Susskind independently proposed something radical, the holographic principle. The insight came from thinking about black hole entropy. Entropy is a measure of disorder of hidden information. The more entropy a system has, the less you know about its exact state. A messy room has high entropy, many possible arrangements of objects that would all look similarly messy. A perfectly organized room has low entropy, only one specific arrangement. Jacob Bekenstein realized in the 1970s that black holes must have entropy, and he found a formula for it. The entropy is proportional to the area of the event horizon, not the volume. This is strange. For everything else we know, entropy is proportional to volume. A bigger box can hold more gas molecules, arranged in more possible ways, so it has more entropy. But for black holes, it's the surface area that matters. The entropy is proportional to the area of the horizon, measured in Planck units. Wyatt Hooft and Susskind's answer was profound because all the information about what's inside the black hole is encoded on the horizon. The horizon is like a holographic screen. Just as a 2D hologram can encode a 3D image, the 2D surface of the horizon encodes all the 3D information about the black hole's interior. This means the interior of the black hole, all the space inside the horizon, has no independent existence in terms of information. It's all encoded on the boundary. If this is true for black holes, maybe it's true for all regions of space-time. Maybe the universe itself is holographic. Maybe all the information in a volume of space is actually encoded on the boundary of that volume. This sounds like science fiction, but in 1997, Juan Maldatina provided concrete mathematical evidence. he discovered a precise correspondence, now called ADS CFT, between a theory of quantum gravity in a space and a quantum field theory on the boundary of that space. Two completely different descriptions of the same reality, one with gravity in a higher dimension, one without gravity in one fewer dimension, both giving identical predictions for any measurement. This is one of the most important discoveries in theoretical physics in the last 50 years. It suggests that holography is a fundamental principle of quantum gravity. What does this mean for information? It means that information falling into a black hole doesn't truly disappear. It gets encoded on the event horizon, scrambled perhaps, hidden in subtle correlations, but preserved. When the black hole evaporates through Hawking radiation, the information gradually comes back out. Not obviously, not in a way you could easily decode, but it's there in the precise correlations between different Hawking photons. The information is preserved. The paradox is resolved, or at least we have a promising path toward resolution. But this raises new questions. If the interior of a black hole is encoded on the horizon, what does that mean for the experience of falling in? When you cross the horizon, you feel nothing special. You seem to enter a real three-dimensional space. Yet according to holography, you're somehow on the horizon. This leads to strange puzzles, like the firewall paradox proposed by Almeri Marov-Polchinski and Sully in 2012. They showed that preserving information seems to require a wall of high-energy particles at the horizon, which contradicts the equivalence principle, which says you should feel nothing special at the horizon. These puzzles are still being worked out, but the holographic principle remains our best hope for resolving the information paradox. If the universe is holographic, what does that mean for reality? It suggests that the familiar three-dimensional world we experience is in some sense a projection from a lower dimensional description. This is eerily reminiscent of Plato's allegory of the cave. Prisoners chained in a cave see only shadows on the wall cast by objects passing in front of a fire behind them. The shadows are all they know. They take them to be reality, but the shadows are projections. The true reality is the three-dimensional objects casting the shadows. Is our three-dimensional experience a shadow of some deeper, lower dimensional reality? Or perhaps the situation is even stranger. Perhaps both descriptions are equally real. The boundary theory and the bulk theory are two ways of describing the same thing. Neither is more fundamental than the other. This resonates with certain ideas in Eastern philosophy. The concept of Indra's net in Buddhism describes reality as a vast web where each jewel reflects all others. Each part contains the whole. Nothing exists independently. David Bohm, a physicist and philosopher, proposed something similar with his idea of the implicate order. He suggested that the universe we perceive the explicate order unfolds from a deeper enfolded reality where everything is interconnected in ways we can't directly perceive. Holography suggests something similar. The information about a region is encoded on its boundary. The interior unfolds from the boundary. Part and whole are intimately connected in ways that violate our usual intuitions about locality and independence. This has implications for consciousness too. If information is fundamentally holographic, if each part contains information about the whole, then perhaps consciousness works similarly. Neuroscience has shown that memory isn't localized to specific neurons. It's distributed across networks. Damage to one part of the brain doesn't erase specific memories cleanly. Instead, memories become gradually less clear as more damage accumulates. This suggests memory is stored holographically in the brain. Each region contains information about the whole just degraded. Lose part of the hologram, and the image becomes fuzzier, but doesn't disappear entirely. Carl Pribram, a neuroscientist, proposed exactly this in the 1960s and 70s. He suggested the brain operates on holographic principles, and he collaborated with David Bohm to explore connections between holographic mind and holographic universe. Speculation, yes, but suggestive speculation. If reality is fundamentally holographic, if information about the whole is encoded in each part, then perhaps every moment of experience contains the entire history of the universe. Not explicitly, not accessibly, but encoded in the subtle correlations and structures. Leibniz's monads, simple substances that mirror the entire universe from their unique perspective, each one reflecting all others, each one containing, in some sense, everything. The black hole's horizon encoding its entire interior, your consciousness encoding your entire life history, each moment containing all moments. These are deep waters. We're at the edge of what can be said clearly. Beyond this point, metaphor and mysticism blend with mathematics and physics in ways that are hard to navigate. But the holographic principle suggests we should take these ideas seriously. Information is more fundamental than we thought, and it's distributed, interconnected, holographic, in ways that challenge our usual notions of part and whole inside and outside self and world. So we return to our merged black hole, ringing down to stillness. It has only 3 parameters mass spin charge. The no-hair theorem says everything else is erased. But we now know that's not quite true. The information is preserved somehow. Where is it? One answer, it's in those 3 parameters. The specific values of mass and spin are what they are because of the specific merger that occurred. Different initial conditions would have produced different final values. In that sense, the final black hole remembers its parents, not with detailed records, but through its essential properties. But this can't be the whole story. The information content of 2 black holes is much greater than what 3 numbers can encode. So where's the rest? According to the holographic principle, it's encoded on the horizon. The event horizon of the final black hole is larger than the sum of the parent horizons. It has more area, therefore more entropy, therefore more information capacity. The information from both parents, plus information about the merger process itself, is encoded in the microscopic structure of the final horizon. We can't read this information. The encoding is maximally scrambled, spread out in quantum correlations that would require measuring the entire horizon to many decimal places to decode. But it's there, in principle. As the black hole eventually evaporates through Hawking radiation, this information comes back out, very slowly, encoded in subtle correlations between Hawking photons emitted over billions upon billions of years. The Page curve, calculated by Don Page, describes how this works. Initially, as the black hole radiates, the entropy of the radiation increases, information seems to be lost. But past a certain point, the entropy starts decreasing again. Information starts coming back out. By the time the black hole has completely evaporated, all the information has been returned to the outside universe. Nothing was truly lost. This is still somewhat controversial. The details of how information escapes are not fully understood. The firewall paradox and other puzzles remain, but most physicists now believe information is preserved even if we don't yet have a complete picture of how. This physics insight parallels something important about memory and identity. We tend to think of memory as storage, like files on a hard drive. The past recorded and filed away, ready to be retrieved when needed. But that's not how memory actually works. Memory is reconstructive. Every time you remember something, you're rebuilding it from distributed pieces. Neurologists have shown that remembering changes the memory. Each recall is a new construction, influenced by your current state, your beliefs, what you've experienced since. Memory is not a recording of the past. It's a present process that references the past, a pattern of neural activation that recreates more or less accurately something that happened before. And memories are not stored in specific neurons. They're distributed across networks. The same neurons participate in many different memories. The pattern of connections, the strengths of synapses, the dynamics of activation, that's where memory lives. This is holographic. Each part of the network contains information about many memories. Damage to one part degrades all memories, somewhat rather than erasing specific ones completely. The black hole is similar. The information isn't stored in some internal structure. It's encoded holographically in the pattern of quantum correlations at the horizon. And as the black hole evolves, radiating, shrinking, changing, that information is gradually released back into the universe, not as discrete files being read out, but as patterns in the correlations of outgoing radiation. Memory as process, not storage. Information as relationship, not substance. Alfred North Whitehead, the process philosopher, described reality in similar terms. There are no static substances, he argued, only events, processes, becomings. What we call objects are actually patterns of events that maintain continuity over time. An object remembers its past not by storing records, but by being the present result of that past. The past doesn't exist somewhere else. It exists in the present as the present. You are not the same person you were 10 years ago. Every atom in your body has been replaced. Your memories have changed. Your personality has evolved. Yet there's continuity. You are the present result of all that past experience. The merged black hole is the present result of its parent black holes and their merger. It doesn't contain them as separate entities, but they live on in what it is now. This is what it means to say information is preserved. Not that there's a perfect recording somewhere, but that the present state contains sufficient information to account for, to be continuous with the past states that led to it. The past is not gone. It's here in transformed form. You are your history, just not in the way you might think. There's another possible resolution to the information paradox, one that seems wild at first, but is taken seriously by many physicists. It comes from the many worlds interpretation of quantum mechanics proposed by Hugh Everett in 1957. In standard quantum mechanics, when you measure a particle, it collapses from being in multiple states at once to being in one definite state. The other possibilities vanish. Information about what could have been is lost. But Everett asked, what if nothing collapses? What if all possibilities are realized just in different branches of reality? When you measure a particle that could be spin up or spin down, the universe splits. In one branch, you measure spin up. In another branch, you measure spin down. Both versions of you exist in different branches, having observed different outcomes. This sounds insane, but mathematically, it's the simplest interpretation of quantum mechanics. You just take the Schrödinger equation seriously and let it evolve forward without any collapse. All possibilities unfold. The universe constantly branches. You never see the branches because once they split, they become independent. The different versions of you can't communicate. Each branch evolves on its own. This preserves information perfectly. Nothing is ever lost because every possibility is realized somewhere. The information is preserved across the multiverse of branches. Now apply this to black holes. When two black holes merge, perhaps the universe branches into many different outcomes. In some branches, they merge one way. In other branches, they merge differently. The quantum uncertainties in the exact geometry, the precise timing, the microscopic details, all of these play out in different ways across different branches. In most branches, the merger happens more or less as we've described. But in some branches, perhaps the black holes don't merge at all. Some quantum fluctuation sends them veering apart at the last moment. The probabilities for different outcomes are determined by the wave function. Most branches follow the most probable path, but all possible paths are realized in some branch. If this is true, then asking what happened to the information might be the wrong question. The information exists in the totality of all branches. Each branch shows one possible outcome, but the complete information is distributed across the multiverse. This is elegant in some ways. It preserves unitarity, the fundamental principle that information is never lost. It requires no collapse, no special measurement process, no mysterious destruction of possibilities. But it comes at a cost. You have to accept that countless other branches of reality exist, forever inaccessible to you. Most physicists find this hard to swallow, not because it's logically inconsistent, but because it seems extravagant. Why should we believe in this vast multiverse of branches if we can never observe any branch but our own? Yet some version of many worlds is increasingly taken seriously. Not necessarily Everett's original formulation, but ideas that the quantum state of the universe describes many parallel realities, all equally real. The black hole information paradox might be telling us that we need to expand our notion of where information can exist, not just in our observable universe, but across all the branches of quantum reality. If many worlds is true, then there are many versions of you right now in different branches of reality. In some branch, you made a different choice this morning, said something different, turned left instead of right. Each small quantum event in your brain leads to a branching, a proliferation of slightly different yous. Most of these branches are nearly identical to the one you're experiencing. The differences are microscopic quantum level, making no practical difference to your conscious experience. But some branches diverge more significantly. In some branch, you made a major life decision differently, took a different job, married a different person, moved to a different city. All of those versions of you exist, living out different lives, completely unaware of each other. This raises profound questions about identity. Who are you really if there are countless versions of you? Derek Parfit explored questions like this in his book, Reasons and Persons. He argued that personal identity is not what matters. What matters is psychological continuity, the connectedness of memories, personality goals across time. If you split into two copies, both with your memories and personality both, are you in the sense that matters? There's no unique you that goes into only one branch. Parfit concluded that we're already multiple in this sense. You now and you, 10 years from now, are connected by continuity, but you're not identical. Every cell has been replaced. Your memories have changed. Your personality has evolved. The I is not a single persistent thing. It's a pattern that maintains approximate continuity over time. And if that pattern branches, both branches have equal claim to being you. This challenges our deep intuition that we're unified, singular beings. But maybe that intuition is wrong. Maybe we're already multiple, just not in ways we usually notice. In every moment, countless possibilities exist for what you might think, feel, or do next. You experience one path through this space of possibilities. But perhaps all paths are real, just in different branches. The illusion of unity comes from the fact that you only experience one branch. From the inside, it feels like a single continuous stream of consciousness. But if many worlds is true, consciousness is constantly branching, proliferating, experiencing every possible path through the quantum landscape of possibilities. Each version of you experiences themselves as the unique continuous I. Each is unaware of the others, yet all are equally real, equally you. This is dizzying, and it might not be true. Many worlds is still controversial, but it's a serious possibility in modern physics, and it forces us to question our assumptions about identity continuity and what it means to be a self. The merged black hole might exist in countless different versions across different branches of reality, each with slightly different mass spin and history. All are real. All are the result of that merger. Yet in each branch, observers see only one outcome. Perhaps identity is always plural, even when it feels singular. We've explored the information paradox from multiple angles. Hawking radiation seems to destroy information. The holographic principle suggests it's preserved on the horizon. Many worlds proposes it's distributed across branches of reality. 50 years after Hawking discovered the paradox, we still don't have a complete, universally accepted resolution. Why? Perhaps because the paradox itself is partly an artifact of how we're asking the question. We assume information is a thing, a substance that exists, that can be stored, moved, or destroyed. We ask, where does it go? But what if information is not a substance, but a relationship? Information is fundamentally about correlation. One thing carries information about another when they're correlated, when knowing the state of one tells you something about the state of the other. The information in a book is not really in the book. It's in the correlation between the arrangement of ink and the meaning those arrangements have for a reader. Without a reader, without that interpretive relationship, the marks are just marks. Similarly, the information in the initial state of two black holes is really information about how that state relates to possible future states, given the laws of physics. When we ask, where does the information go? We're assuming there's a fact of the matter, independent of any observer or reference frame. But quantum mechanics has taught us that reality is observer dependent in subtle ways. Different observers can give different but equally valid descriptions of the same system. Perhaps the information paradox is trying to tell us something similar. From one perspective, an observer outside the black hole, information appears to be lost, then gradually recovered through Hawking radiation. From another perspective, an observer falling into the black hole, the information is never lost. They simply carry it across the horizon. Both descriptions are valid in their own context. The paradox arises when we try to insist on a single, absolute description that works for all observers. This is reminiscent of complementarity in quantum mechanics. Niels Bohr argued that light is both particle and wave, but you can't see both aspects simultaneously. Which description is appropriate depends on what kind of measurement you're making. Similarly, whether information is lost or preserved might depend on your reference frame, on where you're observing from, on what questions you're asking. The deeper truth might be that information is not a fundamental property of reality, but a property of our descriptions of reality. And different descriptions, while seemingly contradictory, can all be valid. Some paradoxes are not meant to be solved, but to be transcended. A Zen koan is not a puzzle to solve through logic. It's designed to short-circuit conceptual thinking, to point beyond language and reason to direct experience. What is the sound of one hand clapping is not a riddle with a clever answer. It's an invitation to stop thinking and start perceiving directly. Perhaps the information paradox is similar. It arises because we're trying to force reality into conceptual frameworks that are too limited. We talk about information as if we know what it is. We talk about preservation and destruction as if these are clear concepts. We talk about inside and outside the black hole as if these are absolute distinctions. But all of these are human constructs, categories we impose on experience to make sense of it. They work well in certain contexts, but in extreme situations near singularities, at event horizons in the quantum realm, these categories break down. Ludwig Wittgenstein argued that many philosophical problems are really just confusions caused by language. We get tangled up in our own words, mistaking grammatical structures for features of reality. Where does the information go? Presupposes that information is a thing that can go somewhere. But perhaps that's already a confusion. Perhaps information is not a thing, but a way of talking about patterns and correlations. And the question of where it goes is as confused as asking where your lap goes when you stand up. Your lap doesn't go anywhere. It's not a thing that can move. It's a configuration that exists in certain conditions and not in others. Similarly, information might not be a substance that needs to be tracked. It's a property of relationships between systems. When the relationships change, what counts as information changes too. The paradox invites us to question our assumptions, not just about physics, but about what it means for something to be real, to exist, to persist through time, in direct experience, before concepts, before language. There's no paradox. There's just this moment, this arising, this pattern of energy and awareness. Two black holes merge. One black hole exists. Information is preserved in the mathematical structure, or it's not. Or the question doesn't apply. The silence before the question is wiser than any answer. In Taoism, The Tao that can be spoken is not the eternal Tao. The name that can be named is not the eternal name. In Buddhism, the finger pointing at the moon is not the moon. In physics, the map is not the territory. Our equations, elegant as they are descriptions. They point to reality, but are not reality itself. Perhaps the information paradox is reality's way of reminding us of this. Our frameworks are useful, powerful, but limited. When they contradict each other, the problem might not be with reality, but with our insistence that reality fit neatly into our concepts. The black hole merges. The information, whatever that really means, does what it does. Reality unfolds, and our equations approximate, describe, point toward it without ever capturing it completely. This is not a failure, it's a reminder. Reality is always larger than our understanding of it, and that's beautiful. Rest here, in the not knowing. The paradox unresolved is wiser than false certainty. Let the question remain open. Let the mystery be mystery. The paradox remains open, unresolved, beautiful in its mystery. We've journeyed far through the physics of collapse and merger, through the philosophy of identity and separation, through the mathematics of information and the silence beyond concepts. We began with a simple question: can two black holes merge into one? The answer we found is yes. Definitively, observably, yes. But the deeper question, what does that yes really mean, has taken us to the edges of understanding, to places where physics and philosophy blur, where equations and experience converge. Now it's time to gather what we've learned, to bring it back from the abstract to the personal, from the cosmic to the everyday. Because this story was never just about black holes. It was always about you, about transformation, about identity, about connection and separation, about what it means to become something new while still being continuous with what came before. The black holes have taught us. Now let's see what their lessons mean for a human life, for your life. Let's complete the circle. Let's come home. Two black holes can merge completely. This is not theory, it's observed fact. LIGO and other detectors have recorded dozens of these events. The gravitational waves carry the signature unmistakably. The process is violent. Massive amounts of energy are released. Space and time themselves are torn and rewoven. The event is catastrophic, in scale the most powerful explosions in the universe since the Big Bang. Yet the result is elegant, simple. A single black hole defined by just 3 numbers, mass, spin, charge. All the complexity of the merger resolves into this beautiful simplicity. The information is preserved somehow, encoded in ways we're still learning to understand. The past doesn't vanish, it transforms. It lives on in the structure of what is now. The universe witnesses and records. The gravitational waves spread outward forever, carrying the story. Nothing happens in isolation. Every event is connected to everything else. 1 + 1 does not equal 2. This is the first lesson. In true merger, in genuine unity, the result is not simply the sum of the parts. It's something new, something that transcends what came before while containing it. Hegel called this Aufheben, a concept that simultaneously means to cancel, to preserve, and to transcend. The synthesis doesn't destroy the thesis and antithesis. It preserves their essential nature while transforming them into something higher. When two black holes merge, they don't exist side by side within a larger container. They cease to exist as separate entities. Their individual horizons dissolve. A new horizon forms. A new identity emerges. You cannot point to which atoms came from which parent black hole. There's no dividing line. The distinction has no meaning anymore. This is true unity, not combination, but transformation. To truly meet another, you must lose yourself. This sounds frightening. It is frightening. The ego, the constructed sense of being a separate, defended self, resists this absolutely. It experiences surrender as death, and in a sense, it is death. The death of separation, the death of the illusion that you are complete in isolation. Martin Buber described this in I and Thou. The deepest relationships are not subject-object relations, not I observing you, I using you, I understanding you as an object of my perception. The deepest encounter is I-Thou, where both I and Thou dissolve into the relation itself, where the space between becomes primary, where neither exists as separate anymore, only as participants in the sacred meeting. This is terrifying and liberating at once. Terrifying because the bounded self must dissolve. Liberating because what emerges is larger, truer, more real than the defended self could ever be. The black holes teach this. They don't orbit forever at a safe distance. They spiral inward. They surrender to the pull. They allow the boundaries to dissolve. And what emerges is not loss, but transformation. A new being, more massive, more powerful, more complex in some ways, simpler in others. In relationship holding, too tightly prevents union. Boundaries, too rigid, block genuine meeting. This doesn't mean losing yourself in unhealthy ways. Codependence where you abandon your own needs, your own reality to please another, is not unity. It's self-erasure, masquerading as love. True unity is different. It's both selves, fully present, fully themselves, yet willing to be transformed by the meeting. The boundaries become permeable without disappearing. You influence and are influenced. You give and receive. You change each other. In meditation, the instruction is similar. Don't try to become someone else. Don't force anything, but also don't cling to who you think you are. Let the boundaries soften. Let the distinction between meditator and meditation dissolve. What remains is not nothing. It's the spaciousness that contains everything. The awareness that was always there before. You divided it into subject and object self, and other inside and outside. The black holes show us this is possible in the most extreme conditions, with the strongest forces, with the most rigid structures. Even there, unity can occur. Boundaries can dissolve. Two can become one. If it's possible for black holes, it's possible for you. A black hole has no features except mass, spin, and charge. The no-hair theorem proves this. Everything else, every detail of how it formed, what fell into it, its entire history, is compressed into these three numbers. This seems like loss. All that richness, all that complexity reduced to a handful of parameters. But look more carefully. Those three numbers are what they are because of that history. The specific value of mass comes from specific progenitors. The particular spin encodes the orbital mechanics of the merger. Every detail influenced the result. So the information is preserved just not in the way we might expect, not as a detailed record you could read out, but as the specific reality of what exists now. The past lives in the present, not as memory, but as structure. What makes you you? Is it your memories? But memories change, fade, reorganize every time you recall them. Neuroscience shows they're unreliable, reconstructive, always being rewritten. Is it your body? but every atom in your body is replaced every few years. The physical substrate is completely different, yet you remain somehow continuous. Is it your personality? But personality changes dramatically across a lifetime. The you at 5 years old and the you at 50 are almost unrecognizably different in temperament, interests, abilities. So, what persists? What is the continuity? Derek Parfit argued that there is no persistent self. What we call identity is just a series of connected moments, each one caused by the previous, but none of them identical to any other. Like a river, the Mississippi River is not the same water from moment to moment. The water constantly flows and changes, yet we call it the same river because of the continuity of the pattern, the banks, the flow. You are a pattern, not a thing, but a process, not a noun, but a verb. The black hole demonstrates this perfectly. After merger, it's not that the two parent black holes are still in there somewhere. They're not. They've been completely transformed, but the pattern continues. The causal chain is unbroken. 3 numbers define the black hole, but those 3 numbers carry all the information that matters. Everything essential is preserved. Everything non-essential has been released. What is essential about you? Not the stories you tell about yourself, not the image you maintain, not the role you play in others' expectations. Something deeper, the pattern of awareness, the capacity to experience, to respond to change, the flow of becoming that you are. Buddhism teaches anatta, no self. Not that you don't exist, but that you don't exist as a fixed, unchanging entity. What you call I is a process empty of inherent existence, dependent on conditions always becoming. This can sound nihilistic. If there's no real self, then what's the point of anything? But it's actually liberating. If you're not a fixed thing, you can change. You can grow. You can let go of patterns that no longer serve. You can transform without losing continuity. The black hole releases everything non-essential. Complexity simplifies. What remains is the essential nature. Mass spin charge. Simple. Powerful. Real. You can do this too. Not through suppression or denial, but through natural release. Let go of the accumulated debris, the old stories, the defended positions, the need to be consistent with who you were. Keep what's essential. Let the rest fall away. What remains is simpler, more you, more real. Even black holes change. They merge. They radiate. Over unimaginably long timescales, they evaporate completely. Nothing in the universe is permanent, not even the most stable, most extreme structures. Everything that exists rose from conditions and will dissolve when conditions change. The black hole seems eternal. Sitting in empty space, it could exist forever. But forever is a long time, and quantum mechanics says even black holes must eventually radiate away. Every structure is temporary. Every pattern is conditional. Everything is process. Anicca is one of the 3 marks of existence in Buddhism. Impermanence. All conditioned phenomena are impermanent. This is not philosophy in the abstract. It's observable fact. Look at anything in your experience. A thought, a sensation, an emotion. It arises, persists for a moment, and passes away. Nothing stays. Even what seems solid and permanent is actually a flow of constant change, happening too slowly for you to perceive directly. The mountain erodes. The ocean shifts. Your body ages cell by cell. Suffering, dukkha. The Buddha taught, comes from clinging to what changes. We want things to stay as they are. We want pleasure to continue pain, to stop loved ones, to never leave ourselves, to never age or die. But everything changes. Clinging to permanence in an impermanent world is like trying to grasp water. The tighter you squeeze, the faster it flows away. The solution is not detachment in the sense of not caring. It's acceptance. Letting things be as they are, allowing change to occur naturally, not resisting the flow. Heraclitus said it, "You cannot step into the same river twice." The river changes, you change, everything flows. Every relationship will change. Every phase of life will end. Every version of yourself will be replaced by a new version. This is not tragic. It's how life works. It's how growth happens. It's how anything new can emerge. The black hole merger is a dramatic example of change. Two ancient objects existing for billions of years suddenly and completely transformed. What was becomes what is, irreversibly, totally. Your life has moments like this too. Perhaps not as dramatic, but just as real. Births and deaths, meetings and partings, beginnings and endings. Resisting these changes creates suffering, fighting against reality, against the nature of things. It's exhausting and futile. Accepting change is different from resignation. It's not giving up. It's giving in to what is, to what's real, to the flow of things. When you accept impermanence, paradoxically, you can be more present because you're not spending energy trying to freeze the moment, to make it last, to prevent the inevitable. You can be here fully knowing it will change, and that knowing makes it more precious, not less. The merged black hole will eventually evaporate. In trillions of years, it will be gone. Does that make it less real now? Does that diminish what it is? No. If anything, it makes it more poignant, more valuable. This existence here and now is all there is. And it's enough. The hardest physics and the deepest philosophy. And discovered they point to the same truth: you are not separate. You are not fixed. You are not alone. Tomorrow when you wake, the black holes will still be merging somewhere in the cosmos, spiraling, colliding, ringing down to stillness. The universe continuing its dance of transformation. And you will wake transformed too. Every night is a small death. Every morning, a rebirth. The you who wakes is not quite the same as the you who slept. This is not loss. This is life. Constant becoming. Endless transformation. The river flowing. When you meet another person tomorrow, remember the space between you is not empty. It's alive with potential, with connection, with the possibility of genuine meeting. You don't have to merge completely. That's not the lesson. But you can let the boundaries soften. You can allow yourself to be affected, changed, touched. Every encounter is a small merger. Every conversation, a collision that sends out waves. Every moment of real presence, a recognition of the unity beneath apparent separation. The black holes teach transformation is possible. Unity is real. What seems permanent can change. What seems separate is connected. These are not just ideas to understand. They're invitations to live differently, to hold identity more lightly, to welcome change more readily, to recognize connection more deeply. You are right now merging with this moment. Reading these words, you're being changed by them, however subtly. The boundary between text and reader, between idea and understanding, is dissolving. This is always happening. You're always merging with experience, with time, with life itself. Usually you don't notice. The changes are too gradual, too constant. But sometimes in moments of real presence, of deep meditation, of genuine love, you catch a glimpse. The separation drops away. Subject and object dissolve. There's only this, only now, only being. The black holes have shown you this is possible. Even with the strongest boundaries, the most extreme conditions, the most rigid structures, unity can occur. You are not your boundaries. You are the space that contains them, the awareness that observes them, the process that transcends them. Now let it all settle, like the black hole after ring down. Let the insights sink in, integrate, become part of you without needing to hold them consciously. The knowledge is absorbed not through thinking, but through being, not through memory, but through transformation. Your breathing slows, your thoughts quiet, the distinctions soften, inside and outside, self and other, two and one. All these boundaries useful, in their way now gently dissolving. You are safe, you are held. The universe cradles you as it cradles all things. Two breaths become one breath. The inhale and exhale, a single cycle, breathing you as much as you breathing. Thoughts arise and dissolve like waves. You don't need to follow them. Let them pass. Let them merge back into the silence from which they came. You were never truly separate, not from this moment, not from this breath, not from the vast mystery that holds all things. The black holes have merged, the waves have spread, the universe has witnessed and recorded, and you are part of it all. Always were, always will be, even as you transform endlessly into what comes next. Sleep now, rest deeply, dream that you dance in curved space-time, that you spiral through infinite possibility, that you wake knowing separation was always illusion, the truth was always unity, always love, always this inexplicable, mysterious, perfect presence. Good night. The journey is complete and just beginning. Silence opens, expands, embraces everything. Rest